Good evening. We are now going into the second session of the third chapter, current electricity. I hope you've gone through the first session. Now, this session deals with a very important topic: cells, EMF, internal resistance, and terminal voltage. A cell is your normal battery that you would find in your home, which you would use to light your torch or any other device, your remote. So this is what we have as a cell. It's got a positive terminal, as you know. It's also got a negative terminal. Now, for my explanations, I'm using a simple galvanic cell, which you might have already learnt in chemistry. So let's look at the galvanic cell. A galvanic cell has two electrodes. One is a zinc rod or a metal plate. The other is the copper rod or in the form of a plate. Then we have the electrolyte. Here we have ZnSO4 and we have CuSO4 on the other side. Now, as soon as this zinc rod, this electrode is dipped into the electrolyte, the zinc has a tendency to lose electrons. So, we have zinc atom on the electrode losing two electrons to become zinc ion, the cation. The positive ion is called the cation. Now, on the other hand, what happens to copper electrode when it is dipped into the electrolyte is you have this electrolyte here which will undergo dissociation, and this will be having Zn2 plus as the positive cation, SO4 minus as the negative anion. This electrolyte will dissociate into copper cation and SO4 minus. Now, this copper ion in the electrolyte will take two electrons to become a copper atom. So, you will see that on the left hand side, the zinc electrode has a tendency to lose two electrons, become zinc positive ion, and neutral atoms are present on the rod or the electrode, but these ions will usually dissolve in the electrolyte. So we have this zinc ion entering the electrolyte. On this side, the copper ion, the cation which is present in the electrolyte, is accepting the electrons from the copper atom, from this rod, and becoming a copper atom. And this copper atom, being a neutral atom, will deposit itself onto the copper rod. So as the reaction goes on, the zinc rod losing these ions will become thinner and thinner. The copper rod accepting these copper atoms will become thicker and thicker. So here we have the zinc ions moving into the electrolyte. Here we have the copper ions moving and becoming copper atoms and depositing itself onto the copper cathode. Now what happens here is, in the last chapter I taught you, potential is the work done on unit charge. So for this reaction to happen here, we need energy. So that energy for unit charge for zinc atom to become a zinc ion is what I will denote as the potential V1 of this rod. I am assigning it a positive sign because it is at a higher potential. Since zinc ions are moving into this electrolyte, we know that the charges always move from higher potential to lower potential. So we may take the zinc rod to be at a higher potential than the electrolyte, and therefore I have assigned that plus V1 as a potential of the zinc electrode. Here we know that the copper ions are moving from the electrolyte to the electrode. So electrolyte must be at a higher potential, the electrode must be at a lower potential, because again I repeat, charges move from higher potential to lower potential. And here for the copper rod I am assigning a minus V2, the potential to be a lower potential than the electrolyte, so a minus V2. Now you will see, so there is a potential difference between the two electrodes, that is, this is at a higher potential, this is at a lower potential, and therefore there is a potential difference between the two electrons, and that potential difference will be V1 minus of minus V2, and that potential difference between the two electrodes or between the two terminals of a cell is what I would call as the EMF. Now, what we discussed here is all chemistry, and for our physics part of the chapter, we don't have to know all this. But what I want you to know or understand is, as soon as you get your cell. Now, if I buy a cell, it has been printed on it as 1.5 volt. This 1.5 volt is the potential difference that is existing between the electrodes when your cell is in open circuit. Open circuit means I have not connected this cell to any external circuit. So this cell now does not carry current. If I connect a bulb or a remote across the cell, then I am closing the circuit and there is a current through the bulb as well as through the cell. So here we are taking the case of an open circuit, that is, I have not connected any resistor across the cell and therefore the cell is not carrying current. And when the cell is not carrying current, that is when it is an open circuit, whatever is the potential difference between the two electrodes, that is what I call as the EMF of the cell. And that is what has been printed as 1.5. Now this part is, see, we normally have the simple circuit here we have a cell carrying a current I through an external resistance R. This is normally the simple circuit that we always draw. This cell is what we have shown here, and the bigger line represents the positive electrode and the smaller line represents the negative electrode. Now this galvanic cell, if you now connect through an external circuit, that means I am going to now connect a external resistance which I call as capital R. Now I have closed the circuit, because now the current can have a continuous flow like this. Okay. Now from the anode, where there is an excess of electrons, these electrons will now flow towards the cathode where there is a deficit of electrons, because the electrons are being taken by the copper ions to become copper atom. So copper cathode has a deficit of electrons, zinc has provided this excess of electrons. So these electrons will now move from the zinc electrode to the copper cathode. Conventional current is taken to be in a direction opposite to that of flow of electrons. So we say that the current now flows from the positive to the negative electrode. So that is what is happening in the external circuit connected by a wire and a resistance. Now let's see what will happen inside the electrolyte or inside the cell. Naturally, your current that reaches here must flow in this direction. Now, inside the electrolyte, the charge carriers are the ions. Let's see how the charge carriers move inside the electrolyte. Now, what is happening here is, these copper ions are taking those electrons and becoming copper atom and depositing itself onto the cathode, the copper rod, the electrode. So, there is a deficiency of positive ions here. So the positive ions will now move in this direction to replace the copper ions that have been taken up. So this is the direction in which your positive ions are moving, so that it will replace the positive copper ions that have been taken up by the electrode. Here what's happening is, the positive zinc ions are entering the electrolyte. So in order to balance the charge, we need the negative ions to move in this direction to balance the excess positive charges that are being added into the electrolyte. So the negative ions, called the anions, are moving in this direction. So you will see inside the electrolyte or inside the cell, direction of positive charges, that is the cations, is taken as the direction of current. So this is the direction of current. So here we have electrons, the current moving from the positive to the negative terminal. Inside we have the current moving from the negative to the positive terminal. So now your cell is carrying a current. Now when your cell carries current, the electrolyte offers a resistance or an opposition to the flow of current. That opposition to the flow of current is what you call as the internal resistance of any cell, denoted by a small letter R. Let us see what are the factors that will determine the internal resistance of the cell. External resistance we already know, R equal to rho L by A, and the external resistance determined by the factors, that is resistivity of a material, which depends on the type of material that you use, the temperature of the material. The resistance also depends on the length of the resistor, the area of the area of cross section of the resistance. That is something we already discussed in the last session. What we are now discussing is the internal resistance of a cell, the factors that determine the internal resistance of the cell. First of all, the internal resistance of the cell is dependent on the nature of the electrolyte, because you know this electrolyte is dissociating to give you the positive and the negative ions, which are the charge carriers. And so the number density, which is small n, which we discussed in the last session as a number of electrons per unit volume in a conductor, when it comes to an electrolyte, it is the number of charge carriers in the electrolyte. So it is the number of ions present per unit volume in the electrolyte, that is the number density n. So the nature of the electrolyte, the kind of electrolyte you choose will determine the number density, and that will determine the internal resistance of the cell. Another factor that determines the internal resistance of the cell is the distance between the two electrodes. Because if you have a larger distance between the two electrodes, as these ions are crossing over, more number of collisions will take place, and that means more opposition is offered, and therefore there will be an increase in the internal resistance if there is an increase in the distance between the electrodes. The third factor that can determine the internal resistance is the temperature of the electrolyte, because you know, higher the temperature, greater will be the dissociation. Greater the dissociation, greater will be the number density. So definitely temperature of the electrolyte is a factor that will determine the internal resistance. Also, the area, as you dip the electrodes into the electrolyte, the area of the electrodes that is dipped inside the electrolyte also will determine the internal resistance of your cell. So I hope you've understood the difference between this capital R and the small r. Capital R is something that we already learned in the first session of this chapter. I am now introducing the small r, which is the internal resistance of any cell, that is the opposition offered to the flow of current inside the cell, where current inside the cell is due to charge carriers. Here the current is due to the electrons. So we now have a potential. So now that current is flowing in the cell and the cell electrolyte is offering an internal resistance, there definitely will be a potential drop inside the cell, potential being equal to current into resistance. This potential drop I into small r will be lost in the cell. So the moment you connect your cell to an external resistance, the potential difference, which was originally E, the EMF between the electrodes, will now decrease by a factor I into R, which is a potential drop inside the cell. So if you take 2 points, one point A here and the other point B here, between the 2 points, we have this resistor connected, and by Ohm's law we know that the potential drop across this resistor is I into capital R. So potential difference across the 2 points in the external circuit is I into R, and inside the cell between the two terminals, the effective potential difference or the terminal voltage, that voltage between the two terminals now become E minus IR, because there is a current flowing in the cell. So this is now equal to I into R, because this is the potential difference between the two terminals A and B, between the 2 points A and B in the external circuit, and inside the circuit between A and B we have the potential as E minus IR. So we have our new equation. I into R we know is V equal to E minus IR, which is a very important equation for you to remember in this topic. Now both V and E are potential difference between the terminals of the cell. They are the same quantity, except this EMF is a potential difference between the terminals when it is an open circuit. That is, you have not connected anything. It is open circuit. There is no current through the cell. And V is the terminal potential terminal voltage, which is the potential difference between the terminals of the cell when you have connected it into an external circuit, that is, it is in closed circuit. This EMF or E is actually standing for electromotive force, which is a misnomer, because you would think that EMF is a force, electromotive force, but it is not. It is actually the potential difference between the terminals of the cell. So I hope you have understood each term in this equation. I, of course, the current that flows through the circuit. Small r, the internal resistance offered by the electrolyte. EMF was the potential difference between the two electrodes before we connected the resistance, or before you put it into a closed circuit like this. When it is an open circuit, that means your electrolyte or your cell is not carrying current. But the moment you put it into a closed circuit and your electrolyte and the cell starts carrying current, it is offered an internal resistance. So there is a potential drop within the cell, and therefore the terminal voltage will now become originally what it was, the EMF minus I into R will be the net voltage across the terminals. So this is the terminal voltage V in volt. This is a EMF. Again the potential difference. So its SI unit is still volt, current and the internal resistance. Now you can have, so you will see from this equation that the V, the terminal voltage must always be less than EMF. V must always be less than EMF. When it is an open circuit, there is no current. So in that case, I becomes 0. So IR is 0. Then in that case, you can have V equal to 0. You also can have a case when V greater than 0. Let's see when that is. Here we say that the cell is discharging through the resistor. So if you connect a bulb, you get lighter because your supply, your cell is discharging through the bulb and therefore producing heat energy. Now when your cell has to be recharged at some point of time, your cell is of no use because it has completely lost the charges here. All of these electrons have gone into the cathode and you will have to recharge your battery. To recharge your battery, what you normally do is you use another battery of larger voltage to recharge your battery here, the cell here. So suppose let's say for example, the cell that you were using, the one that I showed you, let's say this is a positive terminal, this is a negative terminal, and let's say this was a 2-volt battery. And while discharging, if we are talking about the discharging that we had just discussed now, we know we have an external resistor through which we are seeing that there is a current that is flowing like this. This was the direction of current and this was your resistance. Outside circuit, the current was from the positive terminal to the negative. Inside, your current was from the negative, that is the zinc rod, to the cathode, that is the copper rod. That is the direction of current. And we got our formula for terminal voltage when there is current as E minus IR. Now, suppose this battery you are going to charge. Let's say you are going to use a battery of a larger charge. So, we have our 2-volt battery, the positive here and the negative here. We are using a larger battery to recharge this one, 2-volt. Now, let's say we are using a 10-volt battery. Whenever you want to charge your battery, the charger's positive must be connected. So, this is the charger. Positive must be connected to the positive of your cell and the negative of the charger is connected to the negative of your cell. Now, what happens in this case is, we have two currents. One current because of this from the positive, it goes like this. But from here, there is another current in this direction, positive to negative. This provides a current positive to negative, like this. Now, definitely this being of a higher potential, the net current will be in the circuit, will be in the direction of the larger battery. Because this is a stronger battery, this is sending a larger current. So, the net current will be in this direction. So, your current will now be flowing in this direction. So, you will see the current inside your cell has now reversed its direction. Current is now from the cathode to the anode, from the copper rod to the anode, to the zinc rod. So, then what happens is the terminal voltage will now become E plus IR because your current has reversed direction. So, changing that sign will be minus of minus and you get E plus IR. So, we have discussed 3 cases. While your battery is discharging, this is the case where your battery is charging. While your battery is discharging, the terminal voltage V across the cell is equal to E minus IR, whereas while charging, your formula will be V equal to E plus IR. So V can be greater than E in the case of charging, V less than E when it is discharging, and in open circuit because there is no current, V becomes equal to E. Now, from this formula, you will see we have this formula here, V equal to E minus IR. This by Ohm's law you know is I into capital R, that is the external resistance, is equal to E minus IR, or I may write E is equal to, bringing this here, R plus small r. From here I get the current in the circuit as E by R plus R. We also from Ohm's law we know this same current is equal to V by capital R. This is something that you know from 10th standard. Terminal voltage by external resistance will give you the current in the circuit. Now I am introducing this new formula where current in the circuit can also be got by dividing the EMF by the total resistance in the circuit, that is the external resistance and the internal resistance of your battery. So I equal to E by R plus R, or I equal to V by R, which you already know. Now when can current be maximum in your circuit is when you have removed the external resistance, that is there is no external resistance connected, or let's say the external resistance is negligibly small. When your external resistance is negligibly small, the maximum current that can flow through your circuit will be E by small r. Negligibly small, so I am neglecting it. So we have E by small r, maximum current in your circuit. So I hope by now it's very clear to you what you mean by the EMF of a cell, the terminal voltage V of a cell, and the internal resistance of a cell. And these are the formulas that you must be very thorough with to do your problems and to do your application questions. Now, the next topic we have is to find the effective EMF if you connect two or more cells in series. A single one like this is called a cell, but sometimes this 1.5 volt is not sufficient to, let's say, light your torch. So what you do is you add one more battery. So then you would have increased the voltage, and so we can if you use more than one cell, then you call it as a battery. Now these cells can either be connected in series or you can connect these cells in parallel. Now let's see what is the effective EMF and the effective resistance when you connect number of cells in series. I am now going to take just two cells. Then let's say this is A, this is point B, and this is point C. And we have the EMF of the first cell as E1, the internal resistance of the first one as R1, and this is E2 with an internal resistance R2. Now since they are in series, they must carry the same current I. If I write the expression for terminal voltage across AC, that is between this point and this point, we only have one cell. See, this is connected to each other. So we only have one cell between these 2 points. So in our formula E minus IR, I will denote this as E1 because we are talking about this cell between the 2 points AC, and this is R1. Current is the same in both the cells because they are in series, so I don't have to denote it with I1. Then terminal voltage between the points VCB should be equal to E minus IR, where we are talking about the EMF of the second cell between the 2 points C and B and the internal resistance of the second cell R2. Now you know voltages in series will get added up. If your cells are or resistors or your capacitors are in series, then the voltages across each one will get added up. So the total terminal voltage between the 2 points VAB from here to here should be VAC plus VCB because they are in series. So that means I'm going to add I'm going to add equation 1 and I'm going to add equation 2. So that now I have E1 plus E2, taking the I common outside, R1 plus R2, which is my equation 3. Right? Now I'm going to find the effective. That means I'm going to remove the two cells, replace it with a single cell whose EMF is the equivalent of these two in series. So then I will have a cell like this between the 2 points A and B, whose EMF is the equivalent of these two in series, and the resistance is the equivalent resistance of these two in series. So this is my cell, and for this cell, if I am going to write my formula, V equal to E minus IR, this cell is connected just like this between the two terminals A and B. So this is VAB, and it is to carry the same current as the original ones. So this is going to be E equivalent minus I into R equivalent, which is my equation 4. Now if I look at equation 3 and 4, the left hand sides are the same. So I may equate the right hand sides. So here I will see that this E1 plus E2 is what I have as the E equivalent. So I may write, comparing the two equations 3 and 4, the E equivalent of two cells in series is going to be E1 plus E2, and the other term minus I is common for both the equations. So naturally this R equivalent must be the R1 plus R2. So we have the R equivalent equal to R1 plus R2. So you have now seen that if you connect two cells in series, the effective EMF will be simply the sum of the two. For example, if this is 3 volt and this is 5 volt, then the effective EMF will be 8 volt. And the resistance also will get added up, R1 plus R2. Okay. Now suppose you have a case. So now you will see the current is in the same direction, positive away from the positive. So current is in the same direction. Suppose I had replaced the second one like this. Here. So then what happens is, this is a positive terminal of E2, and therefore your current is going to go out like this, from here, away from the positive terminal back to the negative. In such a case, if you derive, you will get the equivalent resistance as E1 minus E2, because the two cells are carrying current in opposite directions. The potentials will get subtracted, but the resistance still will get added, R1 plus R2. So this derivation is there in the notes that I have sent you. It is an important derivation to find the equivalent or effective EMF and resistance of two cells in series. The same exercise or derivation you will have to do when you connect two cells in parallel. So our next topic is connecting two cells in parallel and deriving an expression for E equivalent and R equivalent. So let's look at that. We now have two cells which are connected in parallel. The moment you see that they are connected in parallel, you should remember that they must have the same potential difference across them. So terminal voltage of the two cells will be the same. We have this one with EMF E1 and internal resistance R1. This one with EMF E2 and internal resistance R2. A total current I that enters this junction must split into two. One part going like this, the other part entering here. And this current I will call as I1. This current I will call as I2. So I1 gets into the cell, comes here as I1. I2 gets into this cell, comes here as I2. Together they will join as I and leave the two cells. So now we know because they are in parallel, V is the same, but current gets added up. Always in parallel connection, whether you are dealing with capacitors or resistors, you will see in parallel connection the current total I will be equal to I1 plus I2, but the potential will remain the same. So now I want an expression for I1 and I2 because I am going to use I equal to I1 plus I2. So from your equation, V equal to E minus IR, I can get an expression for I as E minus V by R, right? I have brought this here. So E minus V by R, or I can be written as E by R minus V by R. So please remember, in your cell, I is equal to E by R minus V by R, and this equation is what I am going to use for this derivation. Now let me write down the expression for current in the first cell. Using this expression is E1 by R1 minus V by R1. Since V is the same for both the cells, I don't have to denote it with V1 and V2. Similarly, current in the second cell will be E2 by R2 minus V by R2 using this equation for current. The total current I we know is I1 plus I2, and so the total current I may write as I1 is E1 by R1 plus E2 by R2, and this minus V I will take common outside, so that in the bracket I have 1 by R1 plus 1 by R2, and I close the bracket and I will take this as my first equation. Now, if I replace these two cells with a single cell whose EMF is equivalent to the two EMFs here, then I will draw that as E equivalent, R equivalent, carrying the same total current I. So, I replace the two cells with a single cell. So, for this I will write the expression for current using this equation will be E equivalent by R equivalent minus V by R equivalent, which I will term as my equation 2. So you will see for equation 1 and 2, the left hand side is the total current I. So the right hand sides must be equal. So if I compare this equation to this, I should see that this E equivalent by R equivalent is E1 by R1 plus E2 by R2. So I may write E equivalent by R equivalent is equal to E1 by R1 plus E2 by R2. Okay. Now, also when I compare equation 1 to 2, on the right here, the second term, minus V is common. So I can write this 1 by R equivalent, I am not writing the minus V, it's common to both, should be equal to 1 by R1 plus 1 by R2 from equation 1 and 2. Comparing these two equations, I got these two. Now from here, you will see R equivalent. So this is R equivalent. 1 by R equivalent, if I take the LCM, will be R2 plus R1 by R1 R2. So I may write R equivalent is R1 R2 by R1 plus R2. By taking the LCM and inversing it, you will get R equivalent equal to R1 R2 by R1 plus R2. Now I go back to this equation. This equation I want an expression for E equivalent. So from this equation, I may write E equivalent is equal to, I am taking the R equivalent to the right hand side. So this will be R equivalent bracket E1 by R1 plus E2 by R2. So now I've got an expression for E equivalent. So this is going to be equal to R equivalent, I know is R1 R2 by R1 plus R2 bracket. If I take the LCM here, this is R1 R2, and on top I will have cross multiply E1 R2 plus E2 R1 cross multiply. So if I cancel this and this, I get my expression for E equivalent as E1 R2 plus E2 R1 by R1 plus R2. So that is my expression for E equivalent for two cells in parallel, and this is my expression for R equivalent, or that is the resistance, equivalent resistance of two cells in parallel. So both these derivations are very important. Series we found, the EMF simply gets added up. E equivalent is simply E1 plus E2 and R equivalent is R1 plus R2. In the parallel connection, you will see the E equivalent of two cells in parallel will be E1 R2 plus E2 R1 by R1 plus R2. And the R equivalent is the normal resistance, how you would do in parallel, R1 R2 by R1 plus R2. Now, before I end the session, let me just show you what will happen if you have many cells in series. That is, here we have taken only two cells in series and two cells in parallel. For your application questions, you will need to know the equation for current when you have many cells, identical cells in series and many identical cells in parallel. That's what we're going to see now. So imagine we have a case where we have 1, 2 and so on, n number of cells. 1, 2, 3 could be 100 or 200, n number of cells, and this is connected to an external resistance that is capital R. This has EMF E, internal resistance R, E and R, E and R. So all of them are identical. They all have the same EMF. They all have the same resistance. Then the current in the circuit, you know the formula is E by R plus R. This we just did now, the previous session, the previous topic. So E by R plus R. Just now I told you that the equivalent EMF of many cells in series will be simply adding E1 plus E2 and so on. So if you add E n times, you will see that this becomes n times E. There's only one single resistor here, capital R, so that remains like that. R equivalent of many cells in series will be R1 plus R2 and so on. So here all of them are identical, so if you add n times this will now become n times R. So the current in a circuit where you have n cells in series connected to an external resistance capital R will be I equal to NE by R plus N into R, where N is the number of cells you have in series, E is the EMF and small r is the internal resistance of the cell. The same thing, suppose you connect it in parallel. Let's say we have many cells in parallel like this. Cells in parallel 1, 2 and so on up to, let's say there are m cells in parallel like this, all of them identical, having the same internal resistance and the EMF, and they are connected to an external resistance capital R. Okay. Now because they are all connected in parallel, the potential difference, the EMF must be the same. They can't get added up. So here we have the current through the circuit will be E by R plus R is your original formula. E equivalent will be the same because they are all in parallel and they are identical, they will remain the same. So we have no change in EMF because it is identical, and because they are in parallel, they will all have the same potential difference across them, EMF. There is only one single resistance, capital R. This R equivalent, that is 1 by R equivalent in parallel connection will be 1 by R1 plus 1 by R2 and so on up to n times, like this, m of them. There will be m by R, or R equivalent will be equal to R by m. So this will be replaced with an R by m. So the current in a circuit where you have n cells in parallel will be given by the formula EMF, no change, it will still remain as E, divided by R plus R by m. So that brings us to the end of this topic on cells, and please remember it's a very important topic. You must clearly understand what you mean by the EMF of a cell, the internal resistance of a cell, the terminal voltage V, which you are familiar with in class 10 itself as I into capital R, how the three are related as V equal to E minus IR when a cell is discharging through an external circuit. Then how you can find out the effective equivalent EMF and equivalent resistance when two cells are connected in series. Also, when these two cells are connected in parallel, how you can derive an expression for E equivalent and R equivalent. What I discussed in the end is just for application questions and for problems. You don't need to derive any of this, but you need to know the formula for application questions and the problems. Thank you, and we'll do the next session very soon. Bye.